So let us define what the minimum cost spanning tree is, and let's see how we can compute it. The minimum cost spanning tree is essentially a free tree, but with a minimum cost. Suppose G equals B comma E is a connected graph. Any node can be reached from any node, in which each edge E in E has a cost C of U comma V attached to it. Okay. A spanning tree for G is a free tree that connects all the vertices of V. The cost of the spanning tree is the sum of the costs of the edges in the tree. Okay. And we're looking at for a minimum cost spanning tree. Okay. Typical applications are communication networks, today we have fiber all over the place, and vertices represent the locality where the operator provides you a hubs, and edges represent the links. And cost is primarily the cost of using a particular link. Objective of minimum cost spanning tree. Why do we need a minimum cost spanning tree? Enables quick communication between all vertices. And there are many ways to compute minimum spanning trees. Most use a property called the minimum spanning tree property. Let's see what this is about. What is this property? Let G equal to B of E, B comma E, and is a connected graph. Okay. Let C of U comma V give the cost of each edge. Now, let U be a proper subset of V. If U comma V is an edge of lowest cost from U to V minus U, then it must be included in the tree. Okay. This is very easy to prove. You can use a proof by contradiction as before. Suppose it wasn't. So you have the set U and V minus U. You have a vertex to another vertex V here is an edge. And let's say another vertex edge U prime comma V prime. Suppose there is no MST that includes the lowest cost edge. Includes the lowest cost edge U. Okay. Then there must be some other edge U prime comma V prime. Okay. Such that U prime, which connects them, because we are talking about a free tree and V prime belongs to V minus U. So now if I delete, suppose we delete U prime comma V prime, then before that, if there's another U prime comma V prime, suppose we include UV now, then clearly it must form a cycle. Form a cycle. So what is it that we're looking at? We're looking at a free tree that exists, which does not include the edge UV. Okay. And we're saying, if I take the same U and V minus U, it should be connected by some edge between U prime and V prime. Okay. Now what we're saying is, let's connect UV. Let's connect to this free tree that is there. Let us include UV. If I include UV, what will happen? Then clearly there will be a cycle that will be formed. So what we can do is, if we delete now U prime comma V prime, this implies we have a spanning tree that is of a lower, that is of a no higher cost. We have a spanning tree prime higher cost than the original. Suppose the original tree was T, that means because C of U comma V, C of U comma V is less than or equal to C of U prime comma V prime. Thus, T prime contradicts the assumption that there is no MST that includes UV. So clearly UV has to be included. All right. There are two popular algorithms for computing the minimum spanning tree. These are the Prim's and Kruskal's algorithm. And clearly all the lowest cost edges must be included. Okay. There are two different ways it starts with. Let's look at Prim's algorithm. You can start with any vertex, okay? Because all vertices must be included in the graph. Suppose we had this graph. And it's an undirected graph. We just make it highly connected so that we get a nice spanning tree out of it. Something like this. And suppose the edges had these weights. Let's say we had something like this. Okay. So basically we have, suppose b equal to 1, 2, n. So what we do is we set a u. The way it works is you start with one vertex being in one set. Then we grow the spanning tree one edge at a time. Okay, let's see how we do this. What we do is at each step, we find the shortest edge, UV, then that connects U and V minus U. And then add V to U, okay, from V minus U. And then remove it from V. So in this, what will I do? I'll take the vertex with, I have to start with vertex 1. So I'll take vertex 3. Okay. Then what do I have? I want to connect it, right? So amongst, so 1 and 3 are connected. So I can connect to either, I can connect either to 6 here, I mean 2 here, 4 here, or from 3 I can connect to 6, 2, 3, 4, 5. Among all these edges, I look at which are the cheapest. I don't go back to 1, of course. 1 is already in the set view. So I'm looking at B minus U. And you find 4 is the cheapest. So what do? I include 4 in the, so I have 1 here. And what was it? It was 1, 2, 6. Sorry. 4 is the cheapest. and the vertex is 6. So vertex is 6. I connect 6. Now 1 and 6 are done. So I've connected 1 and 6. Now next I look for the cheapest way. Then I can go from 1, 3 and 6 to any other vertex. Basically we're looking at connectivity to 2, 4 and 5. And among these the cheapest is 2. So I connect 2 here, connect the vertex 4. Okay. Then what do? I need to connect finally to 2 and 5. Then 2 is the connection to 2 is the cheapest. I connect 2 here. 5. Oh, sorry. Yeah. And finally, I connect to the vertex 5 between 3. So this is your minimum spanning tree. Okay. So how long do we repeat this? Clearly, we repeat this until u minus v is v. Okay, all the vertices are included. So the algorithm for prims can be written like this. G is a type graph, and let's say it gives you a tree, and which is a set of edges actually. Set of vertices. T is a set of edges, which makes up the tree. And let's say u comma v, the vertex. We start by making P as the empty set. We initialize u to 1. Then while u not equal to v, do let u comma v be the lowest cost edge. Such that u is in u and v is in v minus v. Then P is assigned the value of T union u comma v. U is assigned the value of u union. Okay, let us u union v. And that. Okay. And now. See, clearly one important point about this algorithm is this minimum spanning tree property very clearly says that it's a connected graph and all the lowest cost edges must be included. So Kruskal's algorithm does it differently. What it does is, if you go back to the graph, let me redraw the graph again. Yes, and this will use something like your union find algorithm. We'll learn more about it. The reason why I don't want to take away the pleasure of learning that in the algorithms course from better teachers. And 1, 6, 5, 3, 6, 6, 4, 2, 5, and 5. That's what we have. So what this does is, it starts out initially with a set concept, because we know that all the lowest cost edges have to be there. So it takes 1, 2, 3. That's the cheapest. Then the next lowest cost edge is between 4 and 6. Takes it. Okay. Then what it does is the next lowest cost is between 2 and 3. So it creates another set. So what happens is all these are disconnected sets, okay, or disjoint sets, right? Then what is done is once these disjoint sets are there, next what do you have? You find that 4 will join these two sets together. So it will merge these two sets. And finally, 5 will merge these two sets. Okay. So either way you can do it. So this one requires, so you have initially every vertex is in its own set. Okay. Then you find the lowest cost edge, cost edge, merge sets. And how long do you do this? Until all vertices are included. Um, the time complexity of either of these algorithms can be brought down to E log E if you use a mean. Okay. So stop here. And I'm sure you'll learn more about Kruskal's algorithm because it's going to do, because you what we have to do is each time we merge with the lowest cost edge, for example, in this example here, when I'm merging with 5, um, or what did I do? I started out 2, 3, 2, 5 merged. And then when I'm merging with 5, for example, this is still there could be another edge, which is lower cost, which has not been included, but it may be connecting within the same set. So you have to find, given a particular edge, you have to find out whether it belongs to, for example, here when I'm looking for this edge 5, I look at whether it belongs to any of these sets. It doesn't belong to any of these sets, therefore it connects between a pair of sets and include it in the graph. Okay. And then of course that means what I'm merging. Merging means what? Remember we did this array representation of trees can be used to merge where we modify parent pointers. So let's stop here and continue tomorrow.